Welcome back. This is the multivariable calculus screencast, and this is the ye olde final, where we will run through an old final exam and talk about its solutions as a means of reviewing. I suppose it's also the last screencast for the semester, so good luck. So let's dive right in here with our practice exam. Now remember, download this from the Canvas site. The resolution here might be a little weak for us. It's good if you can follow along and pause where you want to pause. So dive into this first one. We've got a particle moving through a force field, minus y, x are its components, right, from the origin to the point 1, 1 along this curve. The funny thing is the curve has a lambda in it. We're not going to let that bother us, though, and we want to find the work done, right? So that's just a line integral through a vector field. So you might get cute here and try a Green's theorem or something, but that's not a closed curve. It's not conservative either, so we can eliminate E. Just parameterize the path. It's the graph of a function, so it's pretty simple to do. We've got the components t and t lambda. Right. The x input, we just make our parameter in the output. Y is the output. T. Great. It's a work integral. It's a line integral of a vector field. We are going to need the derivative r prime of t. There it is. All right, first component 1, second component lambda t to the lambda minus 1, plain old power rule. We need to evaluate f on our curve. All right, so we just plug these values for x and y into our vector field f. They work out kind of nicely, right? We get minus t to the lambda t, and when we dot that with r prime, the powers work out just right. We get minus t to the lambda plus lambda t to the lambda. So that just gives us a really nice, simple 1D integral to do from 0 to 1, lambda minus 1 t to lambda. It's just power rule, and you get lambda minus 1 over lambda plus 1, neat little formula there. The second problem is the one that gave students the most difficulty, and it's not a surprise. It's about regularity. We've got partial derivatives that exist for some function f, but the function is not differentiable. Remember, there's a subtle point that you can have partial derivatives in both directions. The function is not overall differentiable. It means it has no good tangent plane. Is one way of thinking about it. The linearization kind of fails. Okay, so how do you approach a problem like this? Well, the first bit is that the derivatives at the origin have to exist. That can eliminate two of our choices right off the bat. Right? Log is not defined at 0, and absolute values, we know, famously don't have derivatives at 0. So those two are out. All right. Now you might make an argument that we know that there is a differentiable, a non-differentiable function with partials, so you can probably eliminate E. We just have these two weird radical expressions to evaluate. All right. And then by looking at not differentiable, all right, you can then look at the denominator here for this first one, radical 1 plus x squared plus y squared. That thing's perfectly smooth everywhere, actually. All right, the x squared and the y squared and the 1, keep it all positive, so square root's not a problem. This guy's absolutely differentiable everywhere. So we can eliminate that guy. Now the smart move on a timed exam is to just say, okay, I know such a thing exists. D has this funky denominator here. That's got to be it. Pick D and move on. Luckily for here, we have the luxury of time, so let's talk about the theory slightly here, though this is a bit subtle. So we know that the partials exist, right? This function is literally 0 if x is 0 or y is 0. So it's 0 on the axes. That's why the partial derivatives exist. It just sees constants, constant 0 in those directions. What that means is our gradient vector is the 0 vector right here. So if this guy were differentiable, its directional derivative in every direction ought to be 0. I'll say that again, right? So if it were differentiable, since its gradient is 0, every directional derivative should be 0, right? If it's differentiable, we can just dot with the gradient. But look what happens when I try to kind of manually evaluate this guy d11. So that's kind of the directional derivative in the direction 1, 1. It's not a normal vector, but it just brings out a constant. Let's not get too bogged down in that. So it's really this limit, essentially, f of h over h. And you see when you plug in HH. Remember, that's a small multiple of the vector 1, 1. We see we get quite a reduction in the quotient, right? The powers of h cancel exactly. Right? We got an h radical 2 h in the bottom and an h squared on top, and the other h from the derivative 1 over radical 2. Anyway, whatever it is, it's not 0. That guy can't work. All right. There's our not differentiable function. We want 3 is sort of a bit of a relief, straightforward. Right? Which expression is equivalent to the integral below? Right? You can probably guess this is a switching the order problem. You can eliminate the other nonsense answers of B and D, but let's just even do it straightforward. Let's sketch the region of integration. So we know we want a function that goes, it may be hard to read here, from the y is the lower bound of e to the x, and the upper bound is the constant e. So we get this region here, expressed by our iterated integral right here. And then if we were to say switch the order of integration, which is at least 3 of these options are doing, what we really want to do is just find an expression for x in terms of y, meaning the bounds of this region of x in terms of y. The left is easy, it's a constant -1. And for the right, we just invert our function. Right? X equals log y. And I encourage you to do a little sketch of this region, because sometimes it's hard to get the exact bounds right. We see that the lower bound for y is actually 1 over e, so this is our best option, A. For MC4, we got some nice graphs here. We're looking for traces, z traces specifically, of this surface, x squared plus z squared equals 100. Notice it's independent of y, so we're going to get a surface that looks the same for each kind of y slice here. And a quick examination, that's just a circle in the xz plane, radius 10, so it's unnecessary, but we could even sketch a quick surface of it. All right, there it is, running along the y-axis. So clearly the z slices are just going to be pairs of lines parallel to the y-axis. And a quick examination shows you radius 10, right? X equals 10, z equals 0 is the solution. So the only logical answer is C. Jump down now to MC5, not the seminal Detroit rock band, but the innocuous arc length question, or it looks like a theorc length question. Theorc isn't a thing, but the arc length is. So we just want to integrate the length of the derivative, r prime of t. All these answers have the same limits of integration, so nothing trying to trip you up there. Let's just compute r prime of t. In fact, we'll compute the square, just so I don't have to write the square root. So we just differentiate term by term, t cos t. We need the product rule for that one, unfortunately. It's got 2 terms there, so that's going to get squared in the length. The second component, t sine t, product rule again, also gets squared, and then the last component, quite nice, just has derivative 1, so we get 1 there. Now, we don't see that answer in our choices, so we're going to have to simplify it, but we can do it in a smart way. Look at these 2 quadratic terms here, right? They're binomials. So we're going to get a cosine squared in the first term here, and you can just peek ahead. You're going to see a sine squared coming in the second term. So those 2 combined, of course, just give us 1. And the cross terms are here from each. They kind of match up nicely too. So we got -2 times the product of these guys, right? Copy for each order. And same down here. But of course we get the same term, so they just cancel. We get 0. And the last term, again, nice. The signs work out because of the square. Get t squared, sine squared, cosine squared. So we get 1 plus t squared, and then squaring the 1 gives 1. 2 plus t squared. Don't forget to put the radical back, however, and we get our answer B. Starting with MC6, we get a couple of straightforward questions. This first one here, critical point of a smooth function, which one does have a local maximum? This is just second derivative test, nothing fancy about it. We want to compute that quantity D, right, the determinant or this matrix of second parcels. Obviously you get fxx times fyy minus the square of the mixed parcels, right, the Clairaut's theorem. We want that to be positive. There are only a couple of possibilities here, but furthermore, we know if we want a local maximum, the second derivative in x has to be negative. D fits the bill exactly, so just pick it and move on. Over to 7, right? Angle between of intersection in radians between the two planes. Right? The only challenge here is say, okay, angle between planes, and recall that that's the same as the angle between normal vectors. So extract the normal vectors, and find their angle by looking at the dot product of the unit vectors in those directions. In other words, we take the dot product of our normal vectors, 2, 2, 0 in the first case, 2, minus 1 in the second case. Don't let that z fool you. You got to bring it over to find the normal vector. But actually, it doesn't matter even if we screwed it up in this case because you got a 0 here. And as we see, we divide by the lengths. Right? We just get 0 here. Right? This is pretty easy. If you just dot the normal vectors in any lazy way, you see there's 0. That means orthogonal. These planes are at angle of pi over 2. So let's move over to the line integral question. I like these visual ones. We have a line integral through a vector field broken into 4 pieces, one in each quadrant, C1, 2, 3, and 4. We want to find which is the largest line integral. We saw a couple of these in class. So really what you're looking for here is whether the direction of the curve kind of agrees with the vector field, right? You get positive numbers from that dot product. When that happens, when it's kind of opposite directions, you get negative numbers. So if you look here at C1 in the first quadrant, clearly that's going to be negative. It's kind of fighting the wind is what I think of in these cases. This guy moves this way. In the second quadrant, it's more agreeable, definitely going to get positive there. Down below, you see it's kind of a mixed bag, right? These vector fields seem to be sort of, if not orthogonal, close to it. You're not going to get a lot of flow in either of these. Right? It's a good old meh, is what I would call it. Here, so C2 is clearly going to be the largest value for our line integral, so we pick that. And finally, we move to MC9, maximum directional derivative of a function among all unit vectors at the point 3,2. That's just asking one thing. Do you know that maximum directional derivative is the magnitude of the gradient vector? So we evaluate that guy, 2xy x squared, just the partial derivatives of our function, plug in the point 3,2 for x and y. I'm hoping I did that correctly. Here, now I need to evaluate that integral, but rather than squaring 12 and 9, they both divide 3, so I can pull a 3 out. And I get, oh wait, that's that 4, 3 vector, right? Famous for having length 5, right? Pythagorean triple tells me that has a nice magnitude of 5, so our answer is D, 15. Flip the page now to multiple choice 10. We find a projection question. In general, I find it helpful to keep around a little diagram. So we have 2 general vectors, B and A here, and remember how projection fits into this picture. It's sort of the leg of that triangle. It's in the A direction. It's kind of the shadow B along the line through A. So that vector is the projection of B onto A. And so now we can just take this picture really and evaluate these 3 statements. I got that the projection is a scalar multiple of A. Yep, just lengthens it, so that one's good. Next is the formula. This is one you should know. We can rederive it, but you should know that indeed it's multiple of A, and A dot B over A dot A gives us the right answer. Right? If you do it out with cosines of the angle between them. So that one holds. Lastly is this B minus the projection of B. So that is in our picture here, right? It's this dashed line there. Difference between vectors just connects the tips, right? From what do I have to add to the projection to get back to B? Well, it's that vertical line there, and indeed you see that it is orthogonal to the projection itself, right? That's a very, very useful fact. So these all hold there. So choose A, 1, 2, and 3. Scan down now, I see a question with a curve and a set of level curves and a contour plot. Now we did probably see a lot of those put together during the semester, although certainly they do fit in the context of integrating through a gradient field. Right? See, that's what we're trying to do here, taking the gradient field and doing a line integral through the gradient field. Now, one of the reasons we didn't see that a lot is we have this big theorem sitting right there. There it is, FTLI. I knew it was coming, the fundamental theorem of line integral. So it says that this line integral of this conservative vector field, conservative because it is the gradient, of f here is easy to evaluate. We just need to subtract the potential at the endpoints, f of b minus f of a, where those represent the points right on the endpoint of our curve. So I can evaluate those easily enough by looking at my graph. I can ignore the path itself, right? Don't get caught up in that trick. So f of b, if you look at the labeling here, it's 1.4. And then look at a over the other end. The orientation matters. Right, 1.2, and I trust you can do that subtraction. Although sometimes I don't trust myself to do it. 0.2. All right, let's move over to number 12 here. Another straightforward one. We've got a smooth vector field, so it's R3 to R3, and a smooth scalar valued function, R3 to R. So, right, vector field, scalar field, if you like. So which one of these is not valid? This is the Nabla notation, where we see in the first one, that's the gradient of the divergence, right? Remember, so gradient of the divergence is a scalar. We can take the gradient. A is fine. All right. F, vector field, cross the gradient. Gradient's a vector field. We can cross two vectors, so that's fine. Vector cross vector. I'll go out of order here over to D. Nabla dot Nabla looks a little funny, but that's a very, very important operator here. That's the Laplacian, and it does indeed apply to scalar functions, so that one's perfectly valid. Same with the curl of the curl, which is here. All right. I don't know exactly what use that has, but I bet it does in certain contexts. So all that's left is this curl of the scalar function. That's not a thing. We can't make sense of part C, so choose that one. And then down here, you might be put off by radical x e to the y. It doesn't look like a fun function, but then what we're asked to do is simply find the expression that is a linear approximation of f near 4 to 0. Right? Important idea that differentiable functions can be approximated with linear functions. So how do we do that? Well, we need three things. Right? We need the value of the function at 4, 0. So just plug it in. Radical 4 is 2. E to the 0 is 1, of course. Makes that easy. Right? We need the first derivative, or the derivative with respect to x of this guy. And that's easy enough to do. It's just a power rule, right? They treat y like a constant. 1/2 comes out. You get 1 over 2 square root of x, e to the y. Again, evaluate at 4, 0. That's important. We need a actual number here to get our linear function. So we evaluate this guy. We get a fourth. Same trick, even easier for the y derivative. Nothing changes. Treat e like x like a constant again. So that one's 2. And then all that's left is to use the formula for linearization. Start with the value of the function 2, and add the partials times the displacement from the point. That's the only kind of place you can get tripped up. Remember, you need to do x minus 4 here because we're at the point 4, 0, and y minus 0 is sitting out here. All right, so that answer's here, sitting up there. Finishing up the multiple choice here, we have a straight-up vector field question. We have a plot and are asked to identify a formula that matches that plot for the vector field. So we don't have that much detail here, so my usual method for doing this is kind of divide up where I know something about the x and y coordinates, mainly where they're positive and negative, so we just look at the quadrants here. And then what I want to observe is in each quadrant, all right, what's the sign of the individual components, what I'd call the P and Q components of the vector field, right? Pointing in the I direction and the J direction. So in the first quadrant here, I'm going to put a plus down. That's because both the direction of the vector field is positive for both the I direction and the J direction, right? Kind of pointing northeast there. Moving to the second quadrant, we got the kind of a northwest idea. So that's right, negative in the y, negative in the x direction, but positive in the y direction. Right? So what I'd say, P is negative and Q is positive in that quadrant. And looking at the other two and doing the same trick, you see we get plus minus and minus in the last two quadrants. Okay, so how does this help? Well, now notice that the y coordinates are given by these, and they've got particular uniformity, right? They're positive above the x-axis and negative below, right? So everywhere that happens. What function does that? Well, y itself, right, is positive above the x-axis and negative below. That's sort of what the y-coordinate is. So we should look for y in the second component, for the j component. That eliminates two answers right away. switching the game here, looking at the x-coordinate, I see another pattern, but it's kind of got this cross pattern. I got positive in the first and third quadrants, right, for the x component, and negative in the second and fourth quadrant. So what do they have in common? Well, x and y have the same sign in these two, and opposite signs in these two, so it makes perfect sense to look at the product xy, and we'll have exactly that sign distribution for the p component, the first component of my vector field. So let's pick B. There. And we're on to our last multiple choice question, number 15 here. So we've got A, B, C are 3 points in our 3 as position vectors. They're familiar with that. We want to find the expression that the area of the triangle with vertices at these 3 positions. So this triangle is floating in space somewhere, but it's true in spaces. In the plane, connect 3 points, you get non-collinear points, you get a triangle. So a little picture can help us out here. So I got my 3 points there. And the thing that I remember most relevant to this piece, I did all the drawing at once there, sorry, is that the area of the parallelepiped, right, defined by 2 vectors, or sorry, in this case, parallelogram. Parallelepiped is 3-dimensional. This is 2-dimensional polygon. The area of a parallelogram is given by the length of the cross product of its 2 sides. So the important thing to see here is that if A, B, and C are the vertices, the sides are given by the differences, right? B minus A is here, C minus A is here. So their cross product, at least its magnitude, will give us the area of the parallelogram here. Chop it in half to get the triangle, right? And there's only one option involving the difference here. That's B there, right? And so we've solved it. We've come to the end of the multiple choice questions and ready to move on to the free response, which we shan't delay and get going. Free response 1, sort of a generic argument, sort of classic, in that we've got a function in the xy plane, right, or rather its graph, y equals fx, it's greater than 0, so in the positive y part of the xy plane. F is unknown, so we'll leave it as f here, and it's positive for 0 is less than x is less than 2. All right, so S is going to be generated by rotating this curve around the x-axis, and part A says we want to find a parameterization for R of u v for this guy. So be sure to include bounds. So what's going on here? We've got our axes, x and y, and then general points A and B, which we know to be 0 and 2 here. And a curve y equals f of x, right? Unknown but positive. It's above the x-axis here. All right, so now our surface is going to come from rotating this guy around x-axis. So to come out, z would be pointing outward, kind of toward the viewer here. Here's my best quick attempt at drawing the surface in question, one of these vase structures. Right, now this is one of those kinds that we should know how to parameterize. Right, the idea is we're going to track our variable along the axis of rotation. Right, one parameter will track that, and then you notice that the radius is going to of the circle that happens when I circle around that point is just given by the value of the function f here. Right, so that's the radius, and we know how to parameterize a circle. We can use the other parameter as the angle, and use cosine and sine to do that. So let's put that together. R is just R of u v. Since we're going around the x-axis, we'll let that one be u. The radius is f of u at each fixed u point, and we'll use v as an angle measurement. So fu cosine v in the y direction, fu sine v in the z direction. And then we did need to put our limits of integration on here, so we are known that u is between 0 and 2. And v, of course, we want to go completely around the circle, so we'll let v be between 0 and 2 pi. In part B here, we're asked to find a formula for surface area that just involves f. Presumably, we could plug into f, have one integral to do, and compute the surface area of this particular surface. So we start with our formula for surface area. That's a surface integral of a function with respect to surface area. And, of course, that function is 1 if we want to get surface area back out. So remember, this is a surface integral of a scalar function. And so we have a formula to turn that into into our UV space. Remember, D is our domain in UV space. For our parameterization, that special quantity, the length of RU cross RV, right, kind of gives us the stretching factor of our embedding, if you will, of our surface. So we need to integrate that quantity over our U's and V's, right, domain there. So order 1, let's compute that cross product here. Remember, doing cross product for a parameterization, you want to give yourself a lot of room here. So make my big matrix ij k. First, I'll differentiate the parameterization with respect to u. All right, so the first component is just 1, and then it's only the u dependence that I care about. So I get the derivative of f pops up. All right, f prime of u, remember, times cosine v, and v is treated as a constant for partial derivatives. So that's the first RU vector. RV, even easier because we can treat u like a constant, so f of u, of course, is a constant. So you get 0 on the first component, and then the familiar minus sign cos. We've probably done that computation 40 times by now. Okay, so this is, remember, just a mnemonic expression. I need to do the cross product if I'm going to find out its length here. So I'll work one component at a time. For the I component, that's the most complicated. I have to sort of cross those two terms. But I get something familiar, right? I see that the cosines cancel out and the sine squareds cancel out to give us 1. The other terms are a little bit easier, j and k, since we have a 0 down here. We just get one term in each. Both of the negative sign, right, fu cos v for j, fu sine v for k. It's not a terrible idea to pause for a second and say, does that make sense as our normal vector? Remember, this is supposed to be normal to the surface. We don't need that geometry in this problem, but it's a good check. So what's happening here? Our normal vector has some dependence on the derivative in the x direction. All right, let's see. F prime of u and f both come into play. That kind of makes sense. How tilted our function is in the x direction will come into play. So it seems to we get that term, and then look in the y and z direction, we see the symmetry here. Again, it's minus fu cos, fu sine. If you recognize, that's the negatives of the actual positions, which makes sense. So this guy's pointing back toward the x-axis, right? It's the negative of the position, so it points exactly toward the x-axis, which makes sense. We should expect to see a component kind of pointing toward or away from the origin, right? So this is our normal vector clearly pointing inside our surface. For this problem, we don't need that, right? We're just going to integrate the length of this guy. So we'll set up our limits of integration, 0 to 2 pi and 0 to 2 for v and u, respectively. Now, when you take the length, notice there's an fu in every component, right? Good old fu there, and there. So when I want the length, since f was considered to be positive, I can just pull that straight out front, and then all I'm left with is the length of this vector of what's left over here. F prime in the first component, and then again I've got cosine sine here, and you know what's happening with this length, right? Cosine squared plus sine squared is 1. So when I take the length, the v dependence is going to drop out, right? The sum of the squares is just 1, no matter what v is. So we can do the v integral. Right? That's why this problem says leave the answer as 1 integral. If I do the v integral, I'll just get 2 pi. Okay? And then what's left, 0 to 2, f of u, and then that funny term which you actually may have seen before in Calc 2, square root of 1 plus the derivative squared. There, it makes sense. You get more surface area for a higher derivative. It gets spread out more when you spin it around. Right. There you go. In free response 2, we arrive at our optimization problem. It says using any method covered in class. I really had 2 in mind that I thought students would use. Some came up with a couple other ones that I accepted, using geometry and tangent planes and such things. But really, my thoughts were that there was either you're going to use unconstrained or constrained optimization. So where does that come up to? The first method would be to parameterize S, right? The surface, this cone that we're looking at. So you parameterize it using 2 variables. We know what a parameterized surface is. And so now what we want to do is kind of minimize the distance, but the distance now is a function of 2 variables, right? U and v. It's just the value of the optimization, r minus the point in question, 1, 1, 0. So notice this is a valid expression. R takes values in R3. I can subtract a 3 vector there, but when that takes length, I get a scalar. So all told, it's a function of 2 variables, spits out a scalar. So this is, we've done this, right? You look for where the gradient of this function is 0. Actually, it's better to square it because to make it smooth near the origin. But this is unconstrained optimization. And there's a question to be presented, but how do we know it's a minimum? Well, this is a distance problem, right? We're looking for a minimal distance between a point not on the set. It's a smooth enough set. We know it has to occur. There has to be a minimum. It's bounded below by 0. Lengths can't be less than, distances can't be less than 0. Clearly it runs out to infinity as we move up the task. So the minimum is going to occur somewhere on this surface. It's going to happen at a critical point. Here. Well, I'm going to leave the details to you to work out for this version of events. The hard part is the parametrization, but then you've got a relatively easy set of equations to solve, right? Just gradient of this f is 0. Instead, I'm going to talk about what I was, the second method I thought people would go for, good old Lagrange multiplication. And this really is on the nose, 3-dimensional Lagrange multiplication if we set up our function of 3 variables to be exactly the distance, right, to the point 1, 1, 0. Right? That's the thing we want to minimize. But of course, our x, y, z's are constrained. We have to stay on some level surface. Again, squared will get us a nice result. So the constraint, though, is being on the surface itself, which we can turn into a level surface of this 3-dimensional function. Right? That's the key there. Subtract over the x and y, and we get z squared minus x squared minus y squared is 0. That's a level surface of this new function g that we're defining. That's Lagrange multipliers. Right? Function to be optimized, a constraint. So go ahead and compute away. Let's first find the gradient of f. Everything's squared and nice, so we just get a 2 comes down, 2x minus 1, 2y minus 1, and 2z. Put that 0 there. And then we need to do lambda times the gradient of g. That's just as easy. Just watch your signs there. All right, negatives on the x and y. So it's a really nice system of equations to solve. It's going to be pretty easy to do. I hope your eye goes to the last line first. All right, I've got 2z is lambda 2z. There's only 2 possibilities to solve a equation like that there. Either z is 0. It could happen, but if z were 0, on the cone, we'd be at the tip of the cone, and we got a feeling that that's not the closest point here. So it's not going to be z equals 0. And if z is not 0, we can divide. We find out that, right, we find out that lambda has to be 1 here. So that's our guy. We've solved for lambda. Plug it in. We get simple equations in the other variables. X minus 1 is minus x after the 2 cancels. So x is a half. Y looks exactly the same. We get y as a half. And then just plug back into g, right, to get z, or on the cone itself. Z has to be positive, so we'll take the positive root. Right, quarter plus a quarter. Z is 1 over radical 2. So there's your point. And again, it does have to be a minimum. We know it has to occur at a Lagrange point. It's somewhere on our surface. I'm not that concerned on this exam with you doing a full rigorous justification for your optimization problems. It's the setting up, solving and finding the candidate points that I care about. On we go to free response 3 here. We got a vector field. Oh, it's some exponential. It doesn't look great. But then part A says show that f is conservative. So we know what that means. We want to show that big F here is the gradient of some scalar function, little f. We have a test that can help us find out if f is conservative, or at least is a candidate, by looking at the mixed partials. Don't waste time doing that here. It says show that f is conservative, right? It would be ill-posed if it weren't. So let's just go straight and look for that potential function, which is really what we need to do here. It's not sufficient to show that the mixed partials are equal, as we saw in our winding number example. So let's set up our equation. What is f of xy going to be? Well, we start, as usual, we're going to look at the first component of the vector field big F here, that thing, if it is conservative, is the x partial derivative of our little f here. So what we're going to do is take that, and we're going to find an antiderivative where we treat y as a constant here. So sort of anti-differentiation in x. So y squared we can treat as a constant. I've got e to the xy here. That's a simple substitution. Treating y as a constant, you just get a 1 over y. Pops out times e to the xy. You can pause and expand that out if you're not sure where that came from. Then I got the plus 1. That's just becomes just x. And the thing you really need to remember is that we're doing sort of partial anti-differentiation here. So our constant is not actually a constant, but rather it could be any function of y. Right? Any function that's independent of x will evaluate to 0 when we take its derivative, its partial derivative. So we have to consider that possibility. Here it's wrong to omit it. Okay, that's there. So what is g is the next question. Well, that's where we're going to use the second component. Right? We need the second component of our vector field here to be the y partial derivative of little f. So we're going to differentiate our expression, little f, with respect to y. We'll cancel the y's there. And it's pretty straightforward. We need the product rule for the first term, but it's not too bad. We get e to the xy because the y goes away. And then we bring down an x when we differentiate the exponential term here with respect to y, right? And x comes out via the chain rule. So we have xy, e to the xy. The x disappears because it doesn't depend on y, and we just get a g prime of y. G only has one variable, so we differentiate with respect to that. But we want that to be equal to the second component here. So we just put that guy down, right? Just write it out. And then you see, of course, unsurprisingly, because we were told this is conservative, we get a lot of cancellations. In fact, everything on the right side cancels. And so the g prime is 0. And once g prime is 0, that means g itself is a constant, right, up here. And since we're just showing that f is conservative, any potential function will do. We don't need to even do it in this generality here. So pick c equals 0. There's a nice potential function for f. All right, so now that we are armed with that, and we see part B, we should probably keep in the back of our mind that we have a potential function. Maybe we ought to use it, and as we'll see, it's extremely easy to do so. All right, I've got c is given by this ellipse. All right, x squared over 4 plus y squared over 9 equals 0. Traversed counterclockwise, and you might be thinking, oh boy, parametrizing an ellipse. I just don't remember exactly how to do that. That's fairly easy with cosines and sines, but the relief here is that, oh wait, I just showed that f was conservative. This ellipse, of course, is a closed curve, right, traversed counterclockwise. Right? When we put those two things together, the fundamental theorem of line integral should be blaring in your head. Right? If you have a conservative vector field, any loop is going to have 0, right? There's no change in the potential if you go around in a loop where you started from, so the line integral is simply going to be 0 here. And you move over to part 3, and you might be tricked because it doesn't say compute directly, and that may be a mistake of the test writer here. He'll remain nameless, but it doesn't say that, so we could apply the fundamental theorem of line integrals again. Right, here's our curve. I don't need to parameterize that upper half. I know that this work integral, or rather that line integral of this vector field, since it's conservative, is just going to be the potential at the two endpoints, which I know to be 2, 0 and minus 2, 0. Right, there's nothing fancy about it. So I just plug in to my f expression there. Since y is 0, it becomes even quite simple. 2 minus minus 2, which is 4. And there's the total line integral. So as long as you keep your head about you, a bit of a gift there in free response 3. And we're on to the final free response question. Notice this exam only had 4 free response questions, but each were longer with multiple parts. I don't guarantee an exact same format for your exam. Okay, so let's look at this problem. We've got the surface S given by this sort of quadratic here, 1 minus x squared, 1 minus y squared, where x and y have absolute values less than 1. I like this. It's not a perfectly smooth function, but it has a level surface that's a square. Right? If you set that equal to 0, x or y could have absolute value 1. So we get a square. So we get this. When we cut it off there, we get this nice ravioli-looking object, which is pleasing. All right, then we've got some vector field that looks terrible, but may turn out to be all right. So, first part, explain briefly how Stokes' theorem does not directly apply to this surface integral. So I've got a surface integral that I'm interested in. If I want to apply Stokes, that f really has to be recognized as the curl of something. Right? If it's not the curl of something, I can't apply Stokes' theorem. So I can illustrate that quickly by doing a quick computation here by taking the divergence. Right? Why does that work? Well, let's take the divergence. The first component, we just get 6x. The y term drops out because we're differentiating with respect to x. The second component, right, I got minus 6xy. Serendipitously, the 6x's drop out. And so you get 0 there. But in the last component, I get 9 because I'm differentiating with respect to z. So there's my divergence of my vector field f. I get something 9, particularly, that's not at 0. Since that's not 0, f is not the curl of anything. Okay, so think about that for a second. Why is that true? Because the divergence of the curl always leads to 0 of any differentiable vector field. Twice differentiable vector field. Anyway, this one failed that test, right? The divergence is not 0. It can't possibly be the curl of anything. So if it's not the curl, there's no Stokes happening here. So what can we do? Well, we've seen this trick on a few examples in class. We're going to find a different surface integral to do. Namely, in this case, we're going to just take the piece of the plane sort of beneath the bottom piece of the ravioli, if you will. Raviolo. Apologies. So B is going to be the flat piece of the plane, right? The one that I drew up here, B. And in particular, I'm going to orient it downward now because I'm going to close off a region which will subsequently be oriented outward. So if it's going to be outward from the cheese of the raviolo, the normal vector needs to point down on the bottom surface. So n is minus k here. That's the unit normal vector to this flat surface. And so computing a flux through the surface from my vector field f looks daunting, but it's not in this case. Right? We've got so much symmetry. First of all, note that every line integral, every flux integral, can be rewritten in this form, where I'm just taking the vector field f dotted with the unit normal vector. I'm understanding n to be the unit normal vector here, and that dot product as a scalar with respect to surface area is the same as a flux through the surface. Right? Confirm that for yourself if you're still shaky on that one. So let's fill in those things. I did it a little quickly here, but look at f, right? There's just the formula for f as given, and there's 0, 0, minus 1. There's minus k here. Now, if I go to simplify this, right, lots of nice things happen before I ever have to parameterize my surface. Right? Of course, the zeros will kill those terms, as they are. And furthermore, our surface has a z-value, a constant z-value of 0. Right? It's a flat square on the xy plane. So that guy's 0. So we're left with a really easy computation. We're just integrating the constant 9 here. Not totally coincidentally, the same 9, similar 9 up there, but not exactly the same. Right? It's not the divergence here, but I integrate 9 across the boundary. I get 9 times 4, right? Because the surface B has area 4. Right? It's just 9 times the surface area. It's a flat square, 2 on each side, so I get 4. So I get 36 for my flux of this vector field through the bottom. All right, so we turn our attention to the last one. So now it says use the divergence theorem to compute the surface integral. So remember, what does the divergence theorem say? It says that the flux through a closed surface is the integral of the divergence on the inside. S by itself is not closed, but if I add in the flux through B, right, the idea being now the solid ravioli and flux through the entire boundary there, has to be equal to the triple integral of the divergence on the inside. So E represents the cheese, if you will, or filling, spinach, pumpkin, if you go that way. I haven't eaten in a while. Anyway, back to the task at hand. So that divergence we converted, it's a constant, it's 9. This is going to be nice. So we're just going to get 9 times the volume of E. That's So all I have to do is compute the volume of E here, and I'll have all the pieces I need. It's not totally trivial to do, but it's a double integral now because we've got top surface is the graph of a function, right? So I can remember that volume can be computed with a double integral in that case. There's my integrand, and you can certainly welcome to go ahead and compute that out if you like in x and y to practice your double integrals. We can make our lives a little bit simpler by noting this is over that big square b again, like that's the domain of this integral, and because of all the symmetry here we can get away with just doing 1/4 of it, multiplying by 4, so 9 times 4 is 36, and then the clever bit is look at this integrand here. You can't always do this, so be careful, but in this case I'm multiplying a function of x times a function of y, and in those cases on an iterated integral, right, over a rectangle in particular, I could pull this 1 minus x squared out of the y integral, and then I could pull the whole y integral out of the x integral. Right? The result is I've got the same expression twice. Right? Dummy variable, doesn't matter. So I can get away with just doing this one integral and squaring it. Right? You may need to slow down to review why that's justified, but we've seen that phenomenon happen before. So one simple, one variable integral to do. All right, power rule does it for you. 1 minus a third for this guy, and then so that gives us 2/3. Don't forget to square it because we need to square the whole business. 4/9 times 36 leaves us with 16. Right, but don't think you're done. Right, all we have done is computed that total flux. In order to get the integral we want, which is the flux through the top of my surface, I need to subtract. Right, 16 minus the flux out the bottom. So remember, that's what the divergence theorem says. The total divergence to the inside is given by the flow in and the flow out. The difference between those two. And there you have it. So we have negative 20 is our flux through this surface. And so we've completed this final exam, probably in a little bit shorter time than you'll be expected to complete it, but best of luck in your studies. See you later.